This is one of the very important topic, fast Fourier transform. Right, so fast Fourier transform. First of all, we will discuss what are the limitations of DFT technique. Then to avoid those techniques, to avoid those limitations of DFT, another technique is used. So what is the importance of FFT, right? So first of all, I want to write here the drawbacks of, or we can call it as a limitations of DFT, discrete Fourier transform. So discrete Fourier transform converts the time domain to frequency domain. So time domain function should be periodic and discrete time signals, and frequency domain function is also periodic and discrete representation, right? So that's why here generally we have to write always n-point DFT. N-point DFT, that means n number of samples are used. So for n-point DFT, it requires n square complex multiplications. It requires n square complex multiplications and complex multiplications and n into n minus 1, n into n minus 1 number of complex additions here. So for n-point DFT, it requires n square complex multiplications and n into n minus 1 complex additions. Like if it takes n is 8 here, 8-point DFT. So just substitute here 8 square, 64 complex multiplications are required, and 8 into 7, 56 number of complex additions are required. So complex additions, complex multiplications meaning is here complex signal is nothing but it is a vector sum of real and imaginary term. So whenever real terms and imaginary terms are defined, then multiplication of those terms and addition of those terms, those are comes under complex multiplications and complex additions. Because here the complete function is defined with exponential function e to the power of minus j 2 pi nk by capital N. So the complete function e to the power of j theta is nothing but it is a cos theta plus j plus or minus j sin theta. So it has real term and imaginary term is there. Every time it has to perform multiplications operations and it has to perform addition operations. That's why for n-point DFT, n square number of complex multiplications are required and n into n minus 1 complex additions are required. To reduce the number of complex multiplications and additions, FFT technique is used, right? So this FFT technique, fast Fourier transform technique, is used to reduce the number of complex multiplications and number of complex additions. Then how many number of complex multiplications and additions are reduced here? That is explained by one standard formula. That formula explains like this: for n-point FFT, fast Fourier transform, it requires, right? So number of complex multiplications and additions are reduced compared to the DFT technique here. And that after using FFT technique, the number of complex multiplications are n by 2 log of base to n complex multiplications and n into log of base to n complex additions are enough here, right? So to reduce the number of complex multiplications and additions, even and odd function representation is used here. Even and odd functions, that means whatever the samples are there, these samples are divided into two parts, even samples and odd samples. Then even samples are directly performs the addition operations and odd samples performs the subtraction operations. So just now I have explained here one twiddle factor, one circle representation. In that circle, half of the circle it gives the same complex representations, and remaining half of the circle it gives the same with opposite sign. That's why first half of the analysis purpose we have to assume that part as a even, and the remaining analysis we have to take it as a odd function. So here completely we have to convert the complete function into two parts, even function and odd function. So that means dividing. So dividing the complete function into two parts, even and odd. That's why it is also called as radix 2 technique. Radix 2 explains it has two number of possible combinations. So in digital system, number system analysis is there. So in that number system, that radix explains the number of possible combinations of the number system. If the radix is 2, then it has only 2 possible combinations. One is 0 and another is 1. And if the radix is 8, it has 8 possible combinations, that is octal number system. If the radix is 10, it has 10 possible combinations, 0 to 9. So that number system is decimal number system. If the radix of the number system is 16, then it has 16 possible combinations, and the range is from 0 to F, 0 to 9 and A to F. So totally it has 16 possible combinations. So the radix of the number system explains the number of possible combinations in that number system. And similarly here, we have to divide the complete function into 2 parts, right? So the complete function is divided into 2 parts, means it has only 2 possible combinations. That's why this technique is also called as radix 2 technique. Radix 2 technique. See here. Now here 2 types of representations are there. Time domain representation is there, frequency domain representation is there. If you divide this even and odd function in time domain, then it is called a decimation in time technique. And if you divide this even and odd function representation in frequency domain, then it is called a decimation in frequency. So that's why this complete FFT, fast Fourier transform IT, DIT FFT, and one more technique is called diff FFT. DIT explains the decimation in time, right? And diff explains the decimation in frequency. Decimation general meaning is dividing, right? So the dividing even and odd function in time domain, then it is called a decimation in time. And the dividing even and odd functions in frequency domain, then it is called a decimation in frequency. Decimation is nothing but separation or division part, right? So completely we have to divide the complete function into even function and odd function. Only 2 possibilities are required. If you divide that even and odd function representation in time domain, then the technique is called decimation in time, and the division part in frequency domain, then it is called a decimation in frequency. These 2 techniques are again comes under FFT, fast Fourier transform, right? So using FFT, number of complex multiplications and number of complex additions are reduces. That's why now onwards we have to take the k value range. The k range is from 0, 1, 2, 3 up to n by 2 minus 1. So number of complex multiplications and additions are reduces here. In DFT technique, what is the range of k? 0 to n minus 1. So totally it takes the n number of samples. But here we have to take this k value is up to half of the samples. So that's why the k range is changes from 0 to 0, 1, 2 up to n by 2 minus 1. Right? So please take this now. DIT FFT, decimation in time, FFT, fast Fourier transform. It is also called as radix 2 technique. That butterfly diagram is I am writing like this here. So the complete time domain function is divided into 2 parts, even function and odd function. Even function and odd function. So it gives you finally 2 frequency domain equations. So here 2 samples are there. In frequency domain also it expected is 2 samples. Those samples are like this. This odd function is always multiplies with Twiddle factor. This odd function is always multiplies with Twiddle factor. The Twiddle factor is Wn whole to the power of k, right? Odd function always multiplies with Twiddle factor. Then immediately the even function and even function goes in this direction. This odd function both are combined at this point here. So even function is like this and odd function is like this. Compulsory we have to draw the arrow marks because arrow marks explains the direction here. So this is multiplies with 1. What is this function here? Even function. So immediately we have to write here even function xe of n. So this side it gives the plus, and this complete function multiplies with this one. That's why we have to write like this, omega n whole to the power of k x naught of n, right? And similarly now we have to write another representation here, this one. So again the even function combines with odd function, but this odd function here multiplies with minus 1. Here I am taking the plus operation is nothing but even and the minus operation is nothing but odd. That's why compulsory this odd function is multiplies with here minus 1. Then what is the result here? So even function in this direction, so it goes in this direction. So this is even function minus this complete product here, Wn whole to the power of k into odd function. So in decimation in time, first of all we have to divide the complete time domain function into even function and odd function. So first of all we have to divide even function into odd function. So here one time we have to perform addition. Even function adds with a twiddle factor multiplies with odd function, and this even function subtracts with a twiddle factor multiplies with odd function. So this is the standard diagrammatical representation. For easy understanding purpose, just I want to write simple analysis here. Say first of all I am writing this x of k. DFT of x of n is x of k. That is explained like this: n is from 0 to n minus 1. The given function is x of n function. It is multiplied with e to the power of minus j 2 pi nk by capital N. So that complete function now I am writing like this: omega n wn whole to the power of nk. Because just now we have discussed wn twiddle factor is equal to e to the power of minus j 2 pi by n, right? This gives the DFT equation. Now I want to substitute here. This x of n has number of samples are there. First of all I want to substitute even samples and later odd samples, right? So even samples. If you substitute there even samples, right? Even samples. Now the range is reduces here n by 2 minus 1. Even samples I am substituting now xe of n now. Xe of n. So even samples are always explained by like this here wn. Otherwise I will write like this. Even functions, even number of samples are always explained with one standard number, that is 2 into n, and n is replaces as 2 into n whole to the power of k, plus sigma n is from 0 to n by 2 minus 1. Again I am taking n by 2 minus 1. Here I want to take odd. So odd functions number we have to write with 2n plus 1 and omega n whole to the power of 2n plus 1 whole k. So here I want to take even samples and here I want to take odd samples. See, if suppose for easy understanding purpose I am taking here n is 4. N is 4. 4 samples are there. So now the range becomes here 0 to 3. But here it becomes 0 to 1. Substitute here 0, x of 0. And substitute 1, x of 2. So x of 0, x of 2 here it gives here. And later here substitute 0, x of 1. And substitute 1, x of 3. So x of 1, x of 3 here it gives, and x of 0 and x of 2 here it gives. So finally the complete function is divided into even and odd functions, right? Only two possibilities are there. This is I am assuming as even and this I am assuming as a odd. So this representation I am writing like this now. N is from 0 to n by 2 minus 1. See now what is the range here? N by 2 minus 1. So in DFT this explains the 0 to n minus 1, but here we are taking 0 to n by 2 minus 1. So automatically the number of complex multiplications and additions are reduces here, right? So 0 to n by 2 minus 1, this gives the even function into wn whole to the power of k is there. See 2nk. 2nk becomes again nk because this is a periodic representation. So in periodic representation wn whole to the power of k is equal to wn whole to the power of k plus n. After certain time period, after number of samples, again it repeats here, right? So 2 times it increases, so again it becomes omega nk. And later here I am writing like this: n is from 0 to n by 2 minus 1. N is from 0 to n by 2 minus 1. This is completely acts as a odd sample, so odd number of samples. Again I am writing here omega, otherwise I write here 2nk like this. Wn whole to the power of 2nk, and the remaining one more function is there, wn whole to the power of k. See, wn whole to the power of k. So whole to the power of k I wrote outside here. See, odd function multiplies with twiddle factor. So odd function always multiplies with twiddle factor. That part I wrote like this. And here we have to take 0 to n by 2 minus 1. So here whole to the power of 2 is there. This 2 I am writing here. Then the function becomes here omega n is from 0 to n by 2 minus 1 even function into w n by 2. This 2 I am writing directly in division part here. N by 2 whole to the power of nk plus wn whole to the power of k sigma n is from 0 to n by 2 minus 1 x naught of n with w n by 2 whole to the power of nk. Now here the complete function, this explains the even samples and this explains the odd samples. So even samples are the frequency domain function plus omega n whole to the power of k into odd sample frequency domain function. This gives the x of k. If you substitute here, k values are different values. K values are 0, 1, 2, 3. Then one time it gives the positive representation, other time it gives the negative representation. Already I have explained twiddle factor representation. The complete circle, half of the circle it gives the positive values and remaining half of the circles it gives the negative values. So here it gives the positive samples for even function and negative representations for odd function. So that's why this complete representation is we have to write like this here. Now onwards we have to use this representation, radix 2 technique, DIT, decimation in time, radix 2 technique. And here remember this analysis, and sometimes we can write like this: w whole to the power of n by 2 whole k is equal to w whole to the power of n whole k whole square also we can write, or wn 2 into k. So using this analysis here I have wrote n by 2. So that's why the range of the k value is decreases here. Now onwards we have to take the k value is from 0, 1, 2 up to n by 2 minus 1. This analysis is in FFT, fast Fourier transform. So here I have explained simple butterfly diagram of DIT technique, decimation in time. Of n, x of n is, one sequence is given like this: 1, 2, 3, 4. Write k range, right? So write k range here. K range is always explains the k is equal to 0, 1, 2, 3 up to n by 2 minus 1. In this case the k range is 0 and 1, right? And later apply bit reversal. Apply bit reversal. That means we have to divide the complete function into even and odd function. So to divide even and odd functions, representation requires bit reversal operation. So from the bit reversal it gives like this: x of 0, x of 2, x of 1 and x of 3, right? And later write twiddle factor values. So now here the required values are w4 power 0, w4 power 1, because here k value is 0 and 1 is there. That's why I'm writing now w4 power 0 is equal to w2 power 0 is equal to 1. And one more is there, w4 power 1 is j. Sorry, this is w4 power 1. So if you write like this, e to the power of minus j to 5 by 4 whole to the power of 1. So pi by 2. This gives the minus j. w4 power 1 is minus j and w4 power 0 is 1. So we have to find out twiddle factor values according to the k range. K range is here 0 and 1. So only 2 twiddle factors are enough, right? And now from this analysis, the fourth step is required. Draw the butterfly diagram. The fourth step is draw DIT diagram, right? DIT diagram and find x of k. So the fourth step, required step is draw the DIT diagram. The DIT diagram is using 4-point DIT DFT, DIT FFT, right? So to draw that purpose, first of all I am taking now here x of 0 and here x of 2, x of 1 and x of 3. These values we have to take now. Substitute those values. X of 0 according to the given sequence, x of 0 is 1 and x of 2 is 3 and x of 1 is 2 and x of 3 is 4. So this gives the x of 0, x of 1, x of 2, x of 3. These samples write in this order because this technique is decimation in time. The time domain is divided into even and odd functions. So that's why we have to write like this. And later draw the butterfly diagram. That butterfly is 4-point DFT. 4-point DFT. So draw like this. In first stage, so it requires total number of stages are 2 stages. Because already we have discussed 4-point DFT requires two stages. In first stage, this explains the first stage, stage 1. In first stage, one is acts as a even and this is acts as a odd, and this one is acts as a even and here this acts as a odd. So we have to draw like this, right? Then draw the butterfly diagram here, butterfly diagram. This diagram explains the 1 multiplication, so compulsory you have to represent like this. And this is odd function is always multiplies with -1. This is a standard diagram, fixed diagram for all 4-point DFT, and this is multiplies with trivial factor because this is acts as a odd function, even and odd. So odd function is multiplies with trivial factor in first stage. The trivial factor is omega or W2 power 0, right? Similarly in this case also same thing here. Here draw one more butterfly diagram, and this explains the -1, and here trivial factor multiplies. Only one odd function is there, that's why only one trivial factor is enough. And here only one even and one odd, so totally 2 samples are there. That's why you have to take here W2 power 0. So this is finished. Then perform the operation. W2 power 0 value is how much here? 1. This value is 1. Just now we have discussed W2 power 0 is 1, W4 power 0 is also 1. Now 3 into 1 and here 1. So 1 is in this direction and 3 goes to in this direction. These two performs the addition. So already we have discussed the DIT algorithm. Even function, odd function, both are adds here, and in this case it performs the subtraction operation. One time addition, one time subtraction. Then finally, which gives the direct answer here, 1 plus 3 is 4. That part now I am writing here for easy understanding purpose. The stage 1 values I am writing here, right? So x of 0 is 1, x of 2 is 3, and x of 1 is 2, and x of 3 is 4. Try to write in this order. Then understanding is very easy here, right? So one function is 1 plus, and this side 3 into 1 is 3 and it adds 3 here directly, which gives the 4, right? So what is the answer now? Here this gives the 4. Write the answer here like this with arrow mark representation, right? And one more function is, so here 1 is comes in this direction and here minus symbol is there, that's why it performs the subtraction operation. 1 minus 3, this gives the -2. So write the answer here, -2, right? And later similarly here 2 and here 4 is there, so now it becomes here 2 plus 4, this becomes 6, and again 2 minus 4, 2 minus 4, again it becomes -2. So write those answers here, 6 and -2. And already I have explained in 4-point DFT butterfly diagram. So in first stage, individually one function is acts as even, other function is acts as odd and even add. And in next stage, so coming to this stage, these two samples are acts as even functions and these two are acts as odd functions. Odd functions are always multiplied with trivial factor. So that's why immediately we have to multiply with trivial factor here. The trivial factors are here, W4 power 0 and W4 power 1. Because here these two are acts as even and these two are acts as odd. Total number of samples are 4 samples are there. So 4 samples W4, and the range is always k range is from 0 to 1. So that's why we have to take 0 and 1 here. In this case, only one even, only one odd is there. Only one odd is there. That's why we have to take W2 power 0. But in this case, 2 odd functions are there. One function multiplies with W4 power 0 and later one more is multiplies with W4 power 1. Then draw the symbols here. So just I'm indicating like this for easy understanding purpose. So even function and odd functions both are combined like this. Arrow mark explains the 1. This explains the 1. And later draw even and odd function combination. Odd function combines with even function. This is 1 and this is 1, and these two are odd functions, so it is multiplied with a -1. We have to indicate like this. So for easy understanding purpose, I am writing with some other color here. This explains the -1. And here I am multiplying here omega W4 power 0. W4 power 0 is 1 and W4 power 1 is -j. So multiply with that, then which becomes here, this is 6 as it is. And what about this one? W4 power 1 is -j. -j multiplies with -2. -j multiplies with -2. then it becomes plus 2j. This value is here 2j, right? Otherwise, right here, this complete function multiplies with w4 power 0, right? And this complete function is multiplies with w4 power 1, right? Then what is the result here? This result is 4 and this result is here minus 2, and which gives is 6, and here it gives the minus into minus plus 2j, and later perform the operation here. So which operation we have to do here? Even function, odd function, combination, algebraic summation. Towards the upward direction, addition, and towards the downward direction, subtraction. So that's why here in this direction 4 comes here, and from here 6 is there. 4 plus 6, that becomes 10. Otherwise take from here 4 plus 6, 10, and addition of these two, minus 2 plus 2j. See, minus 2 in this direction and plus 2j goes to in this direction. Minus 2 plus 2j. This is acts as a one term. And later towards downward direction we have to write here minus, because minus symbol is there. Perform the subtraction. 4 minus 6. 4 minus 6. What is the value? Minus 2. Right? And again this value is minus 2 and this is 2j. So minus 2j. So now it becomes minus 2 minus 2j. So finally the x of k is, right, x of k is, x of k write in sequence. One value explains the 10, another explains the minus 2 plus 2j, and one more explains the minus 2, and one more explains the minus 2 minus 2j. So finally which gives the 4 samples. So x of n is converted into x of k. So here the advantage is number of complex multiplications and number of complex additions are decreases, because here the k value is 0 to n by 2 minus 1 is there. We are not taking all the samples. With same of the samples, one time we have to perform addition and later we have to perform subtraction. This is the advantage here. And another advantage is here, so the complete diagrammatical representation. So we can find the DFT using diagrammatical representation. So just we have to remember this diagram. Whatever the samples, enter those samples here, then find out the answer. So directly which gives the answer. So write final answer here. X of k, this value is 10 and this value is minus 2 plus 2j, and this is minus 2. This explains the minus 2 minus 2j. So this explains the x of k. Finally, the time domain is converted into frequency domain. And design of these type of analysis using programs and using algorithms are very easy. For this diagram purpose, we have to prepare one separate algorithm. Just we have to give the inputs. So whenever some inputs are corrected, then directly which gives the response, because algorithm does not changes here. For 4-point DFT, the algorithm is fixed, and similarly 8-point DFT is also algorithm is fixed, right? So now here I explained one simple example, how to find DFT of the given sequence. The sequence is here I have assumed 1, 2, 3, 4. Similarly, we have to discuss some other problems. So please take this now.